Welcome to Module 1.5, in which we will cover the bias-variance trade-off. In this module, we'll learn how to analyze the different sources of error in machine learning models, and why balancing bias and variance is critical for building models that generalize well. All machine learning models make mistakes. The key question is, where do these mistakes come from? Two major sources of error are bias and variance. Understanding these helps us explain why models underfit, why they overfit, and most importantly, how we can adjust our models to find the right balance. The prediction error of a model can be broken down into three parts: bias squared, variance, and irreducible error. Bias squared comes from simplifying assumptions in the model. Variance comes from sensitivity to the training data. And irreducible error comes from noise in the data itself, something we cannot avoid. Our job is to reduce bias and variance as much as possible, while accepting that irreducible error will always remain. Bias refers to the error introduced when a model makes overly simplistic assumptions about the data. A high bias model tends to underfit. It cannot capture the true complexity of the underlying patterns. For example, trying to fit a straight line to data that is clearly curved will result in high bias. Another example is predicting house prices using only the size of the house, while ignoring other important features, like location or number of bedrooms. Variance, on the other hand, is the error caused by a model being overly sensitive to small changes in the training data. A high variance model tends to overfit. It learns the noise along with the signal. For example, a deep decision tree may perfectly fit the training data, but perform poorly on new test data. Similarly, a neural network without regularization can memorize the data, instead of learning general patterns. The challenge in machine learning is that bias and variance move in opposite directions as we adjust model complexity. A simple model has high bias and low variance. A very complex model has low bias but high variance. The optimal solution lies in the middle, where bias and variance are balanced, and the total error is minimized. This balance point is what allows models to generalize well to unseen data. To make this concrete, let's look at examples. Linear regression has low variance, but high bias. It's too simple to capture complex patterns. Deep decision trees have low bias, but high variance. They overfit easily. Random forests and regularized models strike a good balance between the two. Neural networks can swing either way, depending on how large they are and how much regularization is applied. These examples show why model selection and tuning are so important. So how do we diagnose bias and variance in practice? If a model performs poorly on both training and test data, it's likely suffering from high bias or underfitting. If it performs very well on training data but poorly on test data, it's likely suffering from high variance or overfitting. A well-balanced model will show good performance on training data and nearly as good performance on unseen test data. To reduce bias, we can increase the complexity of our models, add more features, or use more flexible algorithms. To reduce variance, we can add more training data, apply regularization techniques like L1, L2, or dropout, or use ensemble methods like bagging and boosting. Cross-validation is also a powerful tool to detect and manage variance. The strategy is always to balance both. Too much focus on one side creates problems on the other. To summarize, model error can be decomposed into bias squared, variance, and irreducible error. Bias comes from overly simple models, while variance comes from overly complex models. The trade-off between the two is central to machine learning. Our goal is always to strike the right balance, reducing underfitting and overfitting, so that our models generalize well to unseen data.